Hi, and thank you for having me. My name is Matt Bollinger, and I am a Senior Solutions Architect with Amazon Web Services with a focus in IoT and robotics. I've been with AWS for about 5.5 years, and I've been working with the AWS RoboMaker service since it launched in 2018. Today we'll be talking about how to use RoboMaker to train a robot with reinforcement learning to accomplish a task. And so what we'll be talking about today, really we're going to start with what is AWS RoboMaker and why should you use it. Talk a little bit more about robotic simulations, why they're important, and why they benefit from running in the cloud. And then how to use these simulations to do reinforcement learning to complete a task, whatever it may be. And then finally, we'll end with kind of a demo walkthrough of one of our sample applications so you can kind of learn how to run this yourself and then get started with doing your own reinforcement learning with your own robotics applications. So let's dive right in. So first, we want to talk about why did we build RoboMaker in the first place, and what were the challenges we're trying to address with robotics development? And it all revolves around the speed and difficulty of building robots traditionally. And so we'll start with kind of the biggest problem, I would say, which is building a robot is hard. There's no other way to say it. You require lots of different, very domain-specific expertise to build your robot to be able to accomplish whatever task it's trying to do. So if you take any kind of robot that you're thinking of, you're going to need mechanical engineering skills, electrical engineering skills, computer programming skills, and then machine learning skills to help make the robot smart. And to do all of this requires, a lot of very smart people to do, and you shouldn't have to do it all on your own. And to accomplish this, there are open source frameworks that I'll talk about a little bit later to help address that. And then RoboMaker builds on those to make it easier for you, the end developer, to use and build and create your own robot. So outside of that domain expertise, traditional robotics development is a very time-intensive process because you didn't have cloud scale to be able to build quickly. And so with traditional robots, every time that you would create a new version of your code, you'd have to deploy it to your physical robot or run a simulation, like we'll talk about later, on your laptop. And then once you were doing that, you were kind of had to wait until that was done. And so you couldn't do things in parallel. You couldn't test things out rapidly, and it just took a lot of time. And so being able to move to a cloud model, we're able to look at how do we speed this up, run things in parallel at massive scale, and be able to test quicker. And build these tests into our continuous integration and continuous deployment pipelines to make this just more efficient and speed up that iterative process, more akin to a typical software development lifecycle. Then, um, as I kind of mentioned, when you're doing this development, you have to deploy the software out to the end robot. If you don't have physical robots available to you to test things out, that's obviously a big problem. But also, you might be working with a big or dangerous robot, something that if it were to go wrong, you might damage the robot itself, which could be very costly. Or more importantly, you could damage people or things around the robot. And you don't want to introduce these safety concerns into your development process. So being able to, again, do these simulations just kind of removes that physical hazard aspect and makes the safety and really just the peace of mind of developing a lot better. And then finally, managing robots out in the field, whether from a configuration aspect or just doing code updates out to robots, can be a difficult process if you're not built to handle that ahead of time. So being able to leverage cloud services like AWS IoT and AWS Greengrass, like we do within RoboMaker, makes this a lot easier. And we'll talk about that in a little bit more detail a little bit later. But all of these problems combined really just made robotics development difficult for your average dev or for a lot of development teams in general to kind of tackle the robotics problem. And that's why we developed AWS RoboMaker. So the service can kind of be broken down into three main categories. The first is on the design and development of your robotics application. And for that, we have a set of tools all around being able to do development in the cloud and leveraging cloud tools to speed up the development process. That then goes into being able to test and verify your robotics application using cloud-based simulations. So we'll go into this a lot more detail later, but it's really just the ability to run simulations at scale to run these tests on your robots. And then finally, once you have the application test verified, ready to go, having tools within RoboMaker to do fleet management of robots out in the field and deploy code updates, new versions, new configurations, new tasks to it even, um, leveraging different uh, services like AWS Greengrass, like I mentioned earlier. So first, let's dive into the design and develop side. So there's a couple of things to go over here. If you've done robotics development in the past, some of this might be familiar to you. If not, we'll talk about it a little bit just so you kind of understand some basic concepts. But it's not going to be super important to know for the talk as a whole. But these are things you can definitely look up later if you are interested in robotics and want to get deeper. I'll have some resource links at the end that you can start to investigate. So starting out, um, uh, how do you build your robots in the first place? And so that's where ROS comes into play. ROS is the Robot Operating System, which is an open source framework for developing robotics applications. It's all around making it easier for developers to leverage hardware off the shelf, different machine learning algorithms off the shelf, and bundle them into their own robotics application, whatever it could be. So they don't have to go around writing their own device drivers. They don't have to go around writing their own navigation algorithms, and really just kind of making available all of the different tools that a certain manufacturer or a certain researcher might bring to bear to the broader community and making it easier for you, the developer, to build a robot application. And where this comes into play is that ROS will provide different packages, is what they're called, of those different either device drivers, algorithms, just code that does something that you can then bring into your application, bundle it with the application, and then you're just talking to those different packages over normal ROS topics. And you don't have to kind of build all of this yourself. And now there are different versions of ROS that are available. There's traditional ROS, and then ROS 2, which is in development currently and will be the future of robotics kind of moving forward. But right now, both ROS and ROS 2 are supported by the RoboMaker service. So if you have something that you have built in the past, you can bring that over using ROS Connect or Melodic, two different releases of ROS. And then moving forward, we will be supporting all of the ROS releases in the future. And Amazon is actually actively participating in the development of ROS 2. We're on the board of the development committee and actively contribute to the project and are really invested in the success of ROS 2 moving forward. So a part of ROS for simulations, which we'll talk about a lot later, is Gazebo. So this is a simulation engine that robotics developers use to be able to test their applications. And so this Gazebo engine is what RoboMaker is using to launch these managed simulations. And within Gazebo, you can do a lot of cool things of adding different environments. So walls, objects, different physics, all kinds of different stuff. We'll look at a little bit of it during the demo, but Gazebo in itself is a whole nother topic that we could spend a lot of time on. But just suffice to say for this conversation, it's the physics engine that we're using to run our simulations. And then within those simulations and within ROS itself, there are different kind of development tools that people use to understand what's going on in their robotics application or in their simulation during runtime. And these are things like RViz, RQT, the Gazebo client that are listed here. There's a bunch of other ones, but we'll look at during the demo when we're running the simulation, we can use these native ROS tools in our simulation in our browser to understand what's happening in the simulation itself. So being able to take the tools that ROS developers know and love and apply them to a cloud-based environment just makes that easier for people who have used ROS before to kind of just slide in and use a managed version of that service. And then finally, another part of this development experience is that there is a Cloud9 environment. Cloud9 is AWS's cloud-based IDE. RoboMaker has taken Cloud9 and bundled it with ROS-specific tools, so it comes pre-installed with ROS Kinetic or Melodic when you launch the instance, and also some quality of life tooling to make it easier to interact with the simulation service, which I'll show you later during the demo. And so in addition to kind of these, this development area, as part of ROS itself, we've developed different ROS packages that you can bring into your application, be able to leverage native AWS services without having to write it yourself. And these are things like being able to send ROS bags, which are the logging aggregate of a ROS application directly from your robot to S3. So then it's up there for later analysis or even playback within a simulation if you want to redo something that you saw on the robot. You can use the native package for just shuttling that up to S3. You don't have to worry about it. CloudWatch logs and metrics are also in there. So the output of your robotics application, all of the metrics of, you can do like wheel speed or custom metrics on completing tasks, really anything. A metric is a metric. And logs. So the actual ROS logs that are being generated, you can also shuttle those up to CloudWatch. So they're easy to do for analysis and dashboarding. I have an example of that during the demo that I'll show later. There's also other services that have ROS packages like Kinesis, Poly, Lex. And so these are things for, on the Kinesis side of things, shuttling video. So if your robot has a camera on it, you can then get that camera feed up into Kinesis using Kinesis video streams and then display that somewhere or do processing on that video, something like image recognition in the cloud, and then putting an answer back to sending an answer back to the robot to then act in real time. Or with Lex and Poly, pushing these machine learning capabilities directly to the robot, where instead of having the robot build its own model, you don't have to go around and train your own speech to text or text to speech model that you can then have to shrink down and deploy onto your small robot size. You can then use Lex and Poly that are in the cloud, send the video or send the speech up to the cloud, have it do the processing, and then respond back to the robot. So trying to make it easier for developers to use normal AWS services, machine learning services, or data services on their robots without a lot of development work of their own. And so just quickly on the fleet management aspect, we won't talk a lot about this today, but on this side, it's all around making it easier to handle hundreds or thousands of robots out in the field. And so if you use RoboMaker, there's a development code deployment process as part of RoboMaker that you can use to then push out new versions of your code to your robots and have them update in the field and return back healthy stats and whatnot. So we're not going to go into this a lot today, but that's there in part of the service. So now getting into the real meat we want to talk about is simulations. And so I mentioned some of these, the benefits here earlier, where being able to run simulations just removes the physical aspect of having to deploy your code to a robot, but being able to do so in the cloud just kind of gives you extra benefits on scale, reliability, and really cost effectiveness. Where before, as I kind of mentioned, running a simulation was either on your own laptop and that ate up all your resources, and so you couldn't do any more development there while you waited for your simulation to run. Or larger robotics companies would probably run their own simulation server farms. And that has all of the downsides of what while let them run more simulations and not take up developer resources, running your own server farm for anything is a bummer. That's why I use the cloud in the first place, where you don't have to do all this manual labor of running servers, keeping the environment up to date, all that kind of undifferentiated heavy lifting that everyone who's gone to AWS knows they don't have to do anymore. Same thing applies here with robotics. And so using the managed simulation environment of RoboMaker really just makes it a lot easier to run more simulations, run better simulations, and only do so when you need to. And so with RoboMaker, like all other AWS services, it's pay as you go. And so you're only really paying for when you're running a simulation. And then another benefit there is it being part of the AWS ecosystem. You get all the benefits of CloudWatch metrics, direct service integrations with things like Code Pipeline that just make it easier to develop and iterate faster. And so really why simulations, we'll talk about this in a little bit more detail, is that you're trying to validate that your robotics application works very much like you would a unit test or integration test in a typical software development cycle. And so being able to run simulations in the cloud and at scale really does make it more similar to that unit test or integration test than it has been in the past. Typically, simulations have been something that you do after a long development cycle because it does cost so much to run that simulation. If you can reduce that time and effort cost of running a simulation, you can then start to treat it as an integration test and then include them in your CI/CD pipelines so that you don't have to think about really running it or waiting for it or anything like that. You can now tie these into your CI/CD pipeline, and so after a code commit, I can just commit the code, kick it off, and then my pipeline will then run a set of simulations that will then validate my application. My robot's not going to crash into the wall. It's not going to knock something over. It's not going to break any of that bad stuff before I ever get a push out to an actual robot in the field. And so one of the really good things about being able to run these in the cloud is this reproducible scenario aspect where all of those logs are persisted in S3. And so if I wanted to go investigate why a certain test failed, I can always go back to the logs, replay it, and then watch the simulation happen, see how it goes, and then really understand what's going on with my robots. And so the two other use cases that we're going to focus on today are the training and synthetic data generation sides. So being able to run these simulations, and they're very similar to real world scenarios, you can use the simulations as a training ground for different machine learning models. As we'll see in the demo, what the robot sees in the simulation is very similar to what it would see in real life. And so if I wanted to use the simulated environment to do this training, the data is going to look the same in the virtual world as it will in the real world. And so we can use this to generate large data sets for training our robots without ever having to touch the real world, which just saves a ton on cost, safety, and time. And one of the really cool things with simulations is that since you can run faster in the simulated world, you don't have to do 1 second equals one, like 1 second in the virtual world equals 1 second in the real world. You can do 1 second in the virtual world equals 1 millisecond in the virtual world. And that way you can run these tests very, very rapidly, get a lot of training data, and really refine your model before it ever goes out into a real robot. So going into this a little bit more specifically for what we're talking about today is for reinforcement learning. And for those of you who might not be very familiar with how reinforcement learning works, for our cases, we'll simplify it down. There's a lot more complicated than this, but for our purposes, there's really only two parts we care about today. And that is the agent and the environment. And so in our case, the agent is what it will be determining what the robot's next action is. And the environment is obviously the world that we're in. We'll be talking about the maze later. So it's that maze, and then it's the robot itself. And as the agent is giving actions to the robot, the environment is evaluating, did that action do a good thing for our desired end result or a bad thing? And based off that determination, it will then pass a reward to the agent to say, yes, your actions are doing well, no, your actions are not doing well. And based off of these rewards, the agent is programmed to try to maximize the reward. It wants all of the good things coming back from the environment, none of the bad things. And so when you let this run for a long time, you get this maximization function so that the agent is only doing the good things that furthers its progress towards the goal and none of the bad things. And so one example of this that you might be familiar with is AWS Deep Racer. And so Deep Racer, for those of you who aren't familiar, is a car that we have here, a little RC car that we came out with a couple of years ago to help teach developers this idea of reinforcement learning and doing so in simulation. And we have Deep Racer leagues around the world where you can train your own models for racing around a course and then race other people around the world to see, who has the best machine learning model for driving around this course. And so Deep Racer actually uses the AWS the RoboMaker simulation engine to do its training. So if you've done Deep Racer in the past, this image on the right you'd be familiar with. This is actually a gazebo engine running that Deep Racer is training in. So if you've done this before, you've actually done this already. You've done RoboMaker stuff already. You should know it. But if you haven't done this before, good news is that Deep Racer League will be coming to Bangladesh coming soon, and there'll be more information on this a little bit later in the day. So stay tuned for this, and you'll be able to race people in your local community, which will be a lot of fun. So stay primed on this one, and you'll see more information here. But back to this talk in particular, so the demo that we're going through is kind of a little walkthrough of one of the sample applications we have up on our GitHub page for reinforcement learning and reinforcement training with RoboMaker specifically. So I have the link here and a bit.ly of that same link if it's easier for you to type in. So I'll leave this up here for a second, but really what this example shows is a robot teaching itself to navigate through a maze to a specified goal. So you can see here in the image, and we'll see this in the demo of the robot down in the bottom of the picture, navigating through the maze, and we'll kind of walk through one, how to set this up, and then two, what the simulation itself looks like. And so I'll give you guys another couple seconds to get the link, and then we'll switch over to that demo. Right, so we'll switch to the demo now. Okay, so to make sure that everyone is on the right page, this is what you'll find when you go to that link. This is the page of the sample application that we'll be using. This is the maze runner that, as I mentioned earlier, will have this robot self-learn how to navigate through the maze using reinforcement learning. And so to set this up, what you'll be doing is creating a RoboMaker development environment, which I mentioned before is just a Cloud9 environment that's bundled with some robotics goodness. And what you do is you come in here to the RoboMaker console, create a development environment. I already have one created for today that looks like this once it's created. This is the Cloud9 IDE. And then when you first launch this with RoboMaker, you'll see this welcome page. That's how you know you're correctly on your way. And all you have to do to get this sample up and running is copy and paste these commands. What this is doing is obviously cloning the repo into the RoboMaker environment, which I've done here, and then running a setup script, which is updating all your dependencies for RoboMaker on the instance, bringing in new dependencies that this project depends on, launching and CloudFormation template that sets up the appropriate AWS resources like an S3 bucket, assigning and pulling down subnets for the simulation environment, some of that back office stuff, and then configuring the workspace itself to be able to launch simulation straight here from the IDE. So once that setup script has finished launching, it takes about 20 minutes, just because the first time you build a ROS application, it does take some time to get everything correctly bundled, because that bundle is the application deployment artifact that gets sent to the simulation environment one, but also down to your robot. And so it has all of the code and dependencies that the application needs to run successfully. So it does take some time, but once that's over, you'll be good and ready to go. Now, I've already launched the training simulation. So you can see up here, I have a simulation running. We'll come over here to look at it. This is back in the RoboMaker console. And with the simulation running, I will use these different tools here. So simulation application tools and the robot application tools to see the simulation running in real time. And so I'm using here the Gazebo client, which allows me to look at the simulation world and what's happening in it. And here we can see our robot doing its training run to navigate to the goal. And now this simulation's been running for about 50 minutes. You can see there. And so the robot's doing an okay job. It's avoided the walls at the beginning, but it still has trouble really navigating around and getting to the goal. And so this is going to run for, I have it set up for an hour and a half, but you can set this to run for as long as you want. And with all machine learning, the more data that you have, the better your model is going to be. And so with the hour and a half, going to do okay, and we'll see that when we do an evaluation run. But if I let this run for 8, 9 hours, 10 hours, whatever it might be, our model will be much more precise, based off of just having more data to train against and be good against. So with this in mind of what the robot's doing, let's take a quick look at the code, and if you wanted to play with this yourself, where you can make some changes. And so the most important piece of this project is this runner environments script. And this is what is sending the commands to the robot to do different things. And so there's a lot of ROS specific stuff in here that we won't get into today just for interest of time. But as you get familiar with ROS, a lot of this stuff will look more familiar, such as like the ROS Pi publisher for sending commands to topics and services and all this kind of fun stuff. But what we'll look at right now, in particular, is the agent function that's really doing the rewarding. And so with the application, if you wanted to adjust the reward settings, this is how you'd really start to influence the model and the reinforcement training that it gets, because this is the function that is sending the rewards, those good, bad, or neutral signals to the model to train. And so if I wanted to say, hey, when you get closer to walls, I want you to stay farther away, I could change these reward mechanisms to say, I want you to stay farther away from walls than get closer and cut corners, anything like that. So that's kind of the first part of the code that you want to look at. And the second piece is the launch files. So with ROS, when you want to actually run your robotics application, you start to look at these launch files for what gets launched with the robot. And so with simulations specifically, we're looking at two different launch files. The first simulation that we're running right now, which is the training run, uses this one launch file that uses the training version of our application. And then when we launch the evaluation here in a second, we use this other launch file to specify running the evaluation agent, because the training one is going to create the data. It's going to put our model in S3 such that when we do the evaluation run, we use the model that the training one put in S3, and this is the model, this is the version that we'd actually push to a robot for testing in real life. And then we'd have a different launch file for actual runtime launch. So with this evaluation file, we're only looking to test to see if it works. In our real robot, we'd have another launch file that would actually include all of the code for the for the robot to do whatever application it might be. In this case, if it's maze solving, it could be for actual warehousing or autonomous delivery in a restaurant, anything like that. And so what we have now is we have the training simulation running already, like I mentioned, but now we'll actually run a new simulation for that evaluation. So this new one is going to be, as I mentioned, kind of validating the model, and we'll go and see how far it gets in the simulation to see if we need to run a new training job to actually improve the model over time. So I ran one of these training jobs earlier in the day, so I have a machine learning model already in S3 that this will pull from. And right now, what RoboMaker is doing on your behalf is uploading the robotics bundle and the simulation bundle to S3 so that the simulation job can pull that down, run it all correctly. That's what it's doing all right now. And the simulation job has been created. And so from here, you can see it's preparing. So it's going to take time for the simulation to spin up. But once this goes into running, we'll go over and look at that and understand what's going on in more detail. And so while it's doing that, we'll take a moment to mention that this project is using the coach framework for doing the actual reinforcement learning. And so in the code here, you kind of saw like there isn't anything around creating a model or anything like that. We do that in other parts of the code. So looking at this file for actually setting up the training models. Not going to go into this too much. Wouldn't have time for it in this session. But if you want to look at more of what the model actually is and how it works, you can look at this file here and then look at Coach Platform in more detail. And still, while the simulation is prepping up and getting ready to run, one thing I mentioned earlier is that these simulation jobs, the output of them does go directly to CloudWatch. And so we wanted to look at any of the simulation runs that we've done so far. We can come here to look at the direct output of the robotics application. And so this one is the one that we're spinning up right now. So it doesn't have any logs there. But if we were to look at, say, this one from earlier, you can see the output of our agent, of what it's doing, and see the logs themselves. And so with this one, it's just kind of showing the different steps it's taken, the rewards it's getting from the training, and then once that training's over, kind of the summary of that. Now, the really cool thing that we can do, thanks to the power of CloudWatch and being able to aggregate all of these simulation logs in one place in the cloud, is create CloudWatch dashboards to help summarize what's been happening in our training runs. So this is a CloudWatch dashboard that I put together to kind of show off. It's a very simple example of what you could do with all of these robotics metrics aggregated in one place. And so in here, I just have two simple graphs kind of showing the rewards over time. So you can see in the different runs the improvement that the robot's made over time. So it's starting out with very little reward because it's just immediately running into the wall. And then over time, it improves and then tries new things and is training itself over time. And then down here, it's that same rewards function, but mapped over the number of steps it's taking. And so I create this graph by parsing all of these CloudWatch logs to get the number of steps and the reward functions that it's getting to graph here. And so that combination of being able to pull the ROS logs directly into CloudWatch, thanks to the simulation service, and then be able to graph them here, you can really see over time how one, your code is performing. So you could do a dashboard for number of errors you're getting in your robotics applications, or in this case, seeing model training and performance over time. Both really good options. So with that, our simulation is up and running, and so I can jump from the IDE directly into the console, And this is our evaluation run. We can validate here by seeing the different launch configurations that we specified over in our simulation file or in our simulation run. And then I can open up, as I did before, the Gazebo client to look at the simulation in real time. So here you can see the robot again. There we go. This is using the trained model, so it's performing a lot better than our other one that was still in training to navigate to the goal. And we'll see if it gets there. I don't think it will, based off what we're looking at now. But yeah, so with an hour and a half of training, you can see it got from the start here on a pretty consistent path to this corner, and it would need more training to get around and really get to the goal. So the takeaway from this little demo here is that an hour and a half of training is not enough to have this robot learn how to get to the goal through this maze. But that's what we would take back from this learning and improve our processes over time. And so we'll watch it happen one more time. And with this evaluation, since it's using a pre-trained model, this path is going to be fairly consistent across runs. If we wanted to, we could add different pieces in Gazebo to see how the robot would react. But in this case, we just wanted to see if it got to the goal, and we now know we need more training. And so with that, we'll jump back over to the presentation real quick, just to end it out. Okay, and with that, just a reminder that that example is up on our GitHub page. Here's the link. Both the long link and the bit.ly both go to the repo. So if you want to get hands-on with the demo, there you go. You can go there, start playing with the code. I just kind of showed you how to get it set up and run the simulations and what it looks like. And if you want to get more in depth with it, please go play with the code. Push back any improvements you have. We'll be happy to see what you guys do with it. And with that, to close things out, just kind of reminders that RoboMaker is a great service for doing robotics development. If you're familiar with it already, just the service will help you move faster, iterate quicker, test more frequently, and develop a better robotics project. If you're just getting started with it, please go look at the resources I'll have on the next slide to really get familiar with ROS and with robotics as a whole. And then specifically for reinforcement learning, like we've been talking about today, using RoboMaker simulations at scale in parallel really helps lay the groundwork for reinforcement learning or any kind of machine learning around robotics, for creating data sets, running the testing environments, and then evaluating that those tests actually work. And then just once more, you can try out the demo that we showed today on our GitHub page and get your hands dirty with it. And with that, here are some more resources for you to go learn more if you're so inclined. The first one is just our RoboMaker landing page. From there, you can actually find all the other links and more resources around tutorials and demos and other talks that we've given in the past, just to learn more about the service as a whole. The RoboMaker workshops page is a very good resource for more hands-on workshops with the service around fleet management, your very first robotics application, different ways to use simulated environments outside of reinforcement learning, really driving with how to influence simulations in real time. And then finally, our blog, where we will talk about new ideas and new ways of using the service and building robotic applications with cloud services. And so with that, thank you all for your time. Again, I'm Matt Bollinger. If you have any questions, feel free to reach out to me, and have a great rest of the community day. Thanks again. Bye.